Hello students, we will solve some good questions from structure of atom here. So let me just start with the question. Question says that there is some dissolved water in which there is a dye and light is been falling as photons with a maximum wavelength of 1430 angstroms which is being absorbed and some light is being emitted which is 1580. So fundamentally I want you to understand that when the light falls on any surface, some part will get absorbed and some part will get emitted. Now the lambda absorbed here is given as 1430 angstroms while lambda emitted is given as 1580 angstroms. So far so good. Next, the number of fluorescence quanta is about 53% of number of quanta absorbed, which means number of emitted photons is around 53% of number of absorbed photons. If I write in terms of energy, absorbed energy will be equal to n times of absorbed into hc by lambda absorbed. At the same time, emitted photons energy will be number of emitted photons into hc by lambda em. Now the question revolves around identifying the percentage of absorbed light is emitted as fluorescence. So percentage of absorbed light is emitted as fluorescence light. What percentage of absorbed light is emitted as fluorescence light? In short, we are asked to find E absorbed emission by E absorbed into 100. Right. So to identify this, what I can do, if I can take the ratio of EM by EAB, you would see that NEM by NAB into lambda AB by lambda EM is what we will have, right? Right. So if you see the values here, what values are given? So see the values what we can write here. N M by NAB, that is 53 by 100 multiplied by lambda AB, which is given as 1430, 4530 and 5080. Okay, so this when you solve, this is coming around 0.47. So if we multiply that into 100, so we will get this value into 100 would be around 47%. So I hope you understood that. Okay. Okay, this is a very interesting question where you see it is said that photon of a frequency nu is falling on the metal surface for which the threshold frequency is nu naught. So one thing we know that when you have a photon falling on it with a frequency of nu, and we definitely require certain nu naught to pluck out the electron, and this is the photoelectron which will come out. See, while we are on this case, you got to understand that for every electron to pluck out, we require one photon. Okay. So no matter whatever light you are sending, according to photoelectric effect, what we would see that h nu would be equal to h nu naught plus kinetic energy. Now this kinetic energy is a very interesting term. If you check out, it may so happen that there is a lot of light which might be falling with various different frequencies. So we may have different electrons coming out of it with different kinetic energy. So let's say this is K1, K2 and so on. But there would be one electron coming out with a maximum kinetic energy. And we are in fact only interested in the photoelectrons which are coming at maximum kinetic energy. So this formula in fact is only valid for maximum kinetic energy. Correct? So that is one thing you need to understand. Now let us get back to the options. All ejected electrons have the same kinetic energy, which is incorrect. The ejected electrons have the distribution of kinetic energy from 0 to this part, and which is correct, right? From 0 to this part we will have the kinetic energy. So you can see this is the maximum kinetic energy, which I can write it as h into nu minus nu naught. So this option is right. The most energetic electrons have kinetic energy. No, so that is not the right one, because it is not h nu, it is h nu minus nu naught. The average kinetic energy of ejected electrons. No, photoelectric effect is not for an average kinetic energy. It is only for the maximum kinetic energy. So the option B is correct. See this question now. What is the distance traveled by an electron revolving in the second orbit of beryllium 3 plus ion in 100 revolutions? Okay. So one thing you should recall that time period, normally we define it as 2 pi r by speed of the electron. This is the time period taken for one revolution. So this is for one revolution. So can I say that for one revolution, the distance traveled is 2 pi r. So if at all I take it as 100 revolutions, the distance traveled will be 2 pi r times of 100. So that is the simple logic we'll be using here. So distance traveled will be equal to 100 times of 2 into pi, which I'll take it as 3.14, into r. Can I write that r as 0.529 into n square by z? So here n is 2, because he's asking about the second orbit, and n square by z, which is the beryllium's atomic number, which is 4. This is all in Armstrong, so to convert that into meters, I'll have to multiply 10 raised to the power of minus 10. Now everything is converted into meters. So when you substitute all of these values, we'll get this as around 3.3 into 10 raised to the power of minus 8 meters. Okay, little bit of calculation, but I guess you can get that. Okay, let's see this question now. It says that the speed of electron is given and the distance of electron from the nucleus has to be identified. I think we just have to recall the formula of velocity, which is 2.16 into 10 raised to the power of 6 z by n meters per second. This value is already given to us as 0.547 into 10 raised to the power of 6, and we know the z value is 1 for hydrogen. So from here I can calculate n, which would be equal to 2.16 into 10 raised to the power of 6 divided by 0.547 into 10 raised to the power of 6. Right. So you can see it is almost close to 4. You can closely see that this is around 20 and this is around 5. So n comes to be almost as 4. Next, we have to find out the radius is what is the distance from the nucleus. So which means radius of the nth orbit is 0.529 n square by z in Armstrongs. So that would be 0.529 into 4 square, right? So I think that would come approximately 8.614 Armstrongs. I hope you understood that. So that would be answer C for it. Okay. See the next question here. Now the question says, sir, there are 3 photons which were picked up from the discharge tube, which is 10.2, 12.1 and 1.9. Okay. Which means, suppose if these are all the shell or energy levels, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, energy in the first orbit is 13.6 electron volts minus, and second one is 3.4 electron volts, third one is minus 1.1 electron volts, fourth one is 0.85 electron volts. If you need to know how I am getting it, En is equal to minus 13.6 z square by n square. This is the energy in electron volts. Now check out the energy difference here. The difference between these two is approximately 10.2 electron volts. And if you see the difference between these two, it is around 1.9 electron volts. And the difference between these two is around 12.1 electron volts. I think these are the values he has already given. So suppose if an electron is present in here in this third orbit, it can jump to second orbit and then come to first orbit, thereby creating two photons. So I can get two photons when one electron jumps here. The other way is that electron is already present here and it is jumping here directly, correct? Sorry, that I have considered already. I meant to say electron which is here is directly jumping onto the first orbit. Alright. So for this to happen, how many minimum number of electrons I require? See, if this is electron number 1, it can make two transitions, so I can definitely get this one and this one, these two photons. And this is the second electron. With one transition itself, I'll be able to get this much amount of energy, which means I require only two electrons to get three photons of energy 1.9, 10.2 and 12.1 electron volts. So the answer should be only two atoms, which is needed for us. Okay guys. Next question, it says that when an electron jumps from fourth orbit to the second orbit in helium plus ion, the radiation out should be falling in which particular region? First, let us try to understand this, that delta delta E from N2 to N1, which we write it as E naught into Z square into 1 by N1 square minus 1 by N2 square. Now for Z is equal to 1 for hydrogen atom, we know that if N1 is 1, N2 is 2, N1 is 1, N1 is 2 or N1 is 3. From any higher orbital, if it is falling onto N1 is equal to 1, it is Lyman series and it would be a ultraviolet photon or ultraviolet radiation. This would be Balmer series, which will be in visible region. Third one will be Paschen series, and this would be in infrared region, and so on. I think these three would be sufficient enough for understanding this question. Now the question is, if we take second orbit of helium plus ion, where does that fall into? So now let's see that if delta E, if it is E naught into 2 square, because helium atomic number is 2, into 1 by, from fourth orbit it is coming to second orbit, so 2 square minus 1 by 4 square. Now if you see that this is quite equivalent to the energy of hydrogen atom with this, I'll write it as E naught. If I multiplied that 4 inside, I'll get this as 1 square minus 1 by 2 square, right, which means it is a transition of 2 to 1 for hydrogen spectrum. And we know that for hydrogen spectrum, 2 to 1, anything that comes to 1 is of ultraviolet region. So therefore, photon or radiation will have the energy which would be in ultraviolet region. Okay, so that is a question asked. So which region it would be there? Okay, let's see this question now. In this it's asked like, if Bohr atom or ion is given and only even numbers are considered as the orbit numbers, then what will be the maximum wavelength? Now see, suppose if these are all the various orbits and this starts with 2, 4, 6, 8 and so on, then let's see how we can write nu bar which is equal to 1 by lambda will be equal to RH into 1 by n1 square minus 1 by n2 square. Now if lambda has to be maximum, the transition has to be closest, which means the transition must be from 4 to 2, right? So which means lambda 4 to 2 will be equal to, or I'll just write it as 1 by lambda. So 1 by lambda 4 to 2 will be equal to RH into 1 by 2 square minus 1 by 4 square, which implies lambda max or 4 to 2 would be equal to 1 by RH into, if you see the LCM, this is 16 minus 4, or we can see this 16 and this is 4, so 16 would be common. So 16 minus sorry 4 minus 1, it will be 3 by 16 is what you will have. So that would be reverse of it, right? Because I made that lambda to get inverse. So therefore answer would be lambda max will be equal to 16 by 3 RH. Okay, so that is what is asked. So you can check out which will be answer D. Let's see this question now. It says that one single electron which is in the orbit n, suppose, let's say this is orbit n, from it has gone to some higher orbit. Okay, so I'll just point it this way. So imagine it has gone to some higher orbit. I'll call it as n2. To this higher orbit, now it was at energy x and now it has gone to energy y because electron has excited from this orbit to this orbit. Now during d excitation, which means when this electron is coming back towards this, then it is totally giving 6 different wavelengths. Okay, so I can use the total number of spectral lines formula here, which shows that n2 minus n1 into n2 minus n1 plus 1 divided by 2 will be equal to 6. This is what is given. Now I can say that n2 minus n into n2 minus n plus 1 is equal to 12. So from here I can say n2 minus n is coming as common, so that I'll write as some delta n. So delta n into delta n plus 1 is equal to 12. Okay, so if we solve this, we will get this as delta n whole square plus delta n minus 12 equal to 0. So if we solve for delta n, we will get a positive value of 3. Okay, I'm taking only the positive root out of it. Correct. So now once you get this here, I can say that delta n, which is equal to n2 minus n, is coming as 3, which means it is this n2 which is becoming 3 plus n, which means it has gone to that orbit from n, it has gone to the orbit which is 3 plus n. Therefore the energy which was there when it was in n was 13.6 z square by n square, which is the energy in electron volts, and when it comes to y, which is 13.6 z square by 3 plus n whole square, that is also in electron volts. Now see the options. In all the options he is taking the ratio of xy, so we will take this ratio here also. So we will get this as x by y will be equal to, you can see everything else get cancelled and you'll get n plus 3 whole square by n square. This is what you will have. So if I take root on both sides, we will get this as x by y, which will be equal to n plus 3 by n or 1 plus 3 by n. So if you see the options, 1 plus 3 by n is been matched here. I hope you understood that. Okay, students, let's figure out this question. It says that de Broglie wavelength of a vehicle moving with speed or velocity v is lambda. So lambda dB, we shall write it as lambda 1 is equal to h by p, which is p is the linear momentum, or I'll simply write it as m1 and v1. Now its load is changed so that velocity as well as kinetic energy is doubled now. See, we know that kinetic energy can be written as half into mv square, and here I'll write kinetic energy 1 before it is getting doubled is half into m1 v1 square. Now kinetic energy 2, which is half into m2 v2 square, here the condition given is kinetic energy 2 is twice that of kinetic energy 1, as well as V2 is twice that of V1. So if I put that here, so what I would get this as 2ke1 by ke1. I'm taking the ratio so that things get cancelled. So I'll have m2 2v1 whole square by m1 v1 square. So you can see from here I can figure out m2 would be equal to, rest all are getting cancelled here. So m2 would be equal to m by 2 times m1 by 2 times. So mass has actually become half of it, correct? If the load changes so that velocity is doubled, which means this load, new load, is half the mass of what the original de Broglie's wavelength what was given. So now I need to find out the new de Broglie's wavelength. So can I say that lambda nu would be equal to h by m1 m2 into v2, which is h by m1 by 2 into 2 times of v1, which is h by m1 v1, and h by m1 v1 is nothing but lambda 1, which is the original one. So it shows that there is no change in the lambda. So whatever the earlier lambda was, it is the same thing which was retained. Let's see this question now. We should be calculating the increase in kinetic energy in case if the electron is to decrease its de Broglie's wavelength from 100 nanometers to 50 nanometers. See, we have various formulas here. One thing I can use is lambda dB, which is equal to h by p or h by mv, linear momentum. I can also write this as under root of 2 kinetic energy into m. Okay, this is one thing, but problem is we have to calculate all of this. So the other way of writing it is around 150 by under root of 150 by kinetic energy, right, uh, in electron volts. This is another way of writing, because this comes from the fact that I can write this kinetic energy in terms of mass into this kinetic energy can be written in terms of the voltage difference into charge, correct? So this entire thing, if you take out the charge of electron, mass of electron, this 2h, and multiply everything, you will be able to get this. But this value that comes will be in Armstrongs. So first what we do, let me take lambda 1, which is given as 100 nanometers, and convert that into Armstrongs, which is 1000 Armstrongs. Same thing lambda 2, which is 50 nanometers, I'll write that as 500 Armstrongs. Now I can use this formula directly. So I can write this as lambda 1 is equal to 150 divided by 2 times of kinetic energy, not 2, kinetic energy 1 under root, and lambda 2 is equal to 150 by kinetic energy 2. So if I take just lambda 1 by lambda 2, I will get this as 1000 by 500, which is 2, is equal to under root of this 150 will get cancelled, so I'll be left out kinetic energy 2 by kinetic energy 1. So I will get a relation between these two, right? So I will get this as kinetic energy 2 will be equal to 4 times of kinetic energy 1. So we can find out kinetic energy 1 from here, which is 150 by lambda 1 square. So sorry, that would be equal to 150 by lambda 1 is 1000 Armstrongs. So I'll get this as 1000 Armstrongs here, and this value would be everything in electron volts, right? So that comes to be around 150 divided by how much we got. This kinetic energy which I have is 10 raised to power of 3 here, correct? So I have put all of this comes to be around 1.5 into 10 raised to power of minus 4 electron volts. Correct? Acha, why we are getting this here? Sorry, I forgot to square it. Square, right? Square, yeah. So we got that. And now I can get kinetic energy 2, which will be 4 times of this, which is 1.5 into 10 raised to the power of minus 4 electron volts. The difference of this kinetic energy is what it has been asked, which is kinetic energy 2 minus kinetic energy 1, which would be equal to 4.5 is what I have this common, right? This, because if you see this value, this is around 6 minus 1.5. So that is 4.5 into 10 raised to the power of minus 4 electron volts. Let's check the answer. 4.5 into 10 raised to the power of minus 4 electron volts. You can see the answer B is matching for it. Okay. Okay, let's see this next question. We are asked, like, minimum uncertainty of de Broglie's wavelength of electron accelerated from rest by the potential difference of 6 volts if the uncertainty in the position is given. First, let us use the formula for lambda and find out how much is the value for 6 volts, because you know the formula, this answer would get that in Armstrong. So it is coming as root of 25, which is 5 Armstrongs. Let me put this as equation 1. Now, I want you to remember this, that when it comes to uncertainty of the position, it is actually related with this in equation as delta x dot delta p is greater than or h by 4 pi. But lambda of dB can also be related as h by p, correct? Where p is that linear momentum which we are using. So differentiate this with respect to lambda here. What do we get? So we get this as d lambda is equal to uh, sorry I want p, right? So p will be equal to h by lambda of dB. So now differentiate on both sides, differentiate on both sides. So when you differentiate on both sides, I'll get this as dP is equal to minus h by lambda dB square into d lambda. So if you average out, this would get it as dP will be equal to h by lambda of dB square into delta lambda. So which means I can use this delta p and replace that in terms of delta lambda. So let me put that here. So delta x dot delta lambda, which I write it as h by lambda square dB into delta lambda here is equal to, in a minimum way, it is equal to h by 4 pi, right? So from here I can write this as delta lambda, which is the uh, uncertainty in the de Broglie's wavelength, will be equal to this h. You can see this h will get cancelled here. So we would have this lambda square by 4 pi into delta x. Now lambda we just calculated as 5. So I'll just put that value as 5 square by 4 into pi into delta x. If you check out, it is value is given as 1 by lambda. Oh, but this is in nanometers. So if at all I write this in Armstrongs, you know that this is what you will get. So therefore that would be 10 by pi. So that pi will get cancelled. So we would have around 25 divided by how much is this one? 40. So that is close to 0.625 Armstrongs. So I hope you understood that. So let me check out the value. Yeah, 0.625 Armstrongs. Let's see the next question. It says that orbital angular momentum is given. Let me remind you, OAM, orbital angular momentum, by formula is under root of L into L plus 1 h by 2 pi. This is one thing you should immediately recall before even solving the question. Okay. Next, it says that we have to find out the permissible value of angular momentum for this electron revolving in unknown Bohr's orbit. So which means what should be the value of angular momentum, which is mvr, and you remember from Bohr's model, mvr is equal to nh by 2 pi. So our objective is to find out that n now. So how can we do that? See, we can have this as L into L plus 1 h by 2 pi, and this value is already given as root 3 h by pi. So which means under root of L into L plus 1 by 2 is equal to root 3, which is under root of L into L plus 1 is equal to 2 root 3, or if I square on both sides, I'll get L into L plus 1 is equal to 4 into 3, which is 12. On solving it, I will get L is equal to 3. Okay, so I'm sure you can understand this quadratic equation, which is L square plus L minus 12 equal to 0, which implies L square plus 4L minus 3L minus 12 equal to 0. So you know how to solve this quadratic equation. So you will get only one positive value, that will be L is equal to 3. Now once you get L, see, we know that L is equal to 0, 1, 2, 3. These represents the shape of subshells, where 0 represents for s orbital, 1 represents for p, 2 represents for d, and so on, right? So you can see that if 2 represents for d, then 3 represents for f. So L is equal to 3 represents it is of f orbital. So f orbital in fact starts from 4, right? So you can have 4f, 5f, 6f, and so on. So n could be anything at least 4 or more than 4. So here n should be greater than or equal to 4. So therefore mvr will be equal to nh by 2 pi. So if you see the options, check out for the value which is at least n is equal to 4 or greater than that. Here we got this as 2h by pi. Let me see if there is an option here. Yes, we have 2h by pi. Can we have anything more than that? If you see the other values, they are all less than that only. So obviously they doesn't exist. So only this should be the answer. See this question. The radial probability distribution curve of an orbital of hydrogen has 4 local maxima. If the orbital has 3 angular nodes, then orbitals will be. First, let me write the formulas. Radial nodes of any hydrogen like atom would be equal to n minus L minus 1. Angular nodes will always be equal to L. I think that angular nodes is already given to us as 3. So L value is 3 is what we know. But we have not given the information of radial nodes, but it was given the maximus. For instance, if at all I write it for 1s, you know that 4 pi r square psi square versus r, if at all I write, this would come this way. See, always one maxima represents there are no nodes here. Only if you have two maxima, let's say if I write it for 2s, then it would go touch it and come this way, which means if at all there is one node, there has to have two maxima. Remember this. One node means two maxima. So if at all I have n minus L minus 1 nodes, correct? If it has this many nodes, then these many nodes implies how many maximas? It would be n minus L minus 1 plus 1, because always number of maxima would be 1 more than the number of radial nodes. Therefore, maximum, sorry, number of maximas will always be equal to n minus L, and that value is given to us as 4, and we know L value is given as 3, so therefore n value would be equal to 7. So if n value is 7, right, and L value is 3, so it has to be 7f orbital. So that is what is being asked. So that is the case. The next question, it says which of the following orbital do not exist as per quantum theory? See, for n is equal to 1, we know we have only one subshell, 1s. N is equal to 2, we have 2s and 2p. N is equal to 3, we have 3s, 3p, 3D. Similarly, n is equal to 4, we have 4s, 4p, 4d, 4f. N is equal to 5, we have 5s, 5p, 5d, and 5f, correct, and 6h. And n is equal to 6, we have 6s, 6p, 6d, 6f, 6h, and 6g. So in short, if you check out, S will always start with 1, P will start with 2, D will start with 3, F will start with 4, H will start with, sorry, this is 5, mistake, yeah, H will start with 5, and finally G will start with 6. This is something you can remember. So based on that, can we say 5G exists here? If you check out here, we have 5FG. Okay, I made a mistake here. It is 5G, right? After F, it is G. Then when it comes to G here, this 6G will exist, and then we have 6H. So which means 5G will exist, then 6H will exist. So can you see that 5H does not exist? So only 5G, 4F, 6H, all these exist, but 5H doesn't exist. So that is what is been asked. The next question, here it says that we need to find out which orbital does we have this wave function. See, psi 410, which means it is actually psi, n, l, and ml. So which implies n value is 4, l value is 1, so ml value is 0. See, l value is 1 means p subshell. P subshell will have 3 orbitals, px, py, pz, and pz is conventionally always given as 0. So therefore the orbital which we are looking at is 4pz, correct? So if you check out the options, we have, okay, he didn't even mention z, so it is definitely 4p. Okay, okay, let's see this next question, which says that number of orbitals having n plus l less than 5. So if n plus l has to be less than 5, what are the combinations I can make? N is equal to 4, l is equal to 0, n is equal to 3, l could be what do you say, l could be 1, n is equal to 2, right? When n is equal to 2, l cannot be equal to 2, right? This doesn't exist. But here when l is equal to 1, I can have 0 also, because you just asked less than 5, correct? So that would also be less than 5, n is equal to 3. At the same time, I can have l is equal to 2 also existing for this, right? But here 2 doesn't exist, but 1 can exist, 0 can exist. So 0 and 1 can be existing. So these are all the combinations which we have. So let me write what are all these orbitals which we can make it. So I can have 4s, I can have 3s and 3p, okay? And yeah, oh sorry, cannot have l is equal to 2 here, right? So 3s and 3p, and I can have 2s and 2p. These are the combinations which I can have, right? And finally n is equal to 1 with l is equal to 0, which is 1s. Now let us count, these are all the subshells, and let us count what all the orbitals we can have. We can have one 4s, 3s, 3p, I can have 3px, 3py, and 3pz. Here also 2s, 2px, 2py, 2pz, and here I have 1s. So let me count all the orbitals: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on total I have therefore total of 10 orbitals we have. Alright, so remember, orbitals is the one whose maximum capacity of electrons is 2 electrons. So that is what is asked. So you can see the answer would be D for this. See the next question, we need to find out the set of quantum numbers defining the highest energy in the scandium 1 orbital. Scandium 1, if I write the configuration here, which is scandium plus, which means it is starting from 1s2, 2s2, 2p6, 3s2, 3p6. Now check out, we usually write it as 4s2, but one electron has gone, so it will become 4s1 and 3d 1, right? So this is what we have. Now if you recall the energy of all the orbitals, right, so the way I have written is the energy based on off-post rule. So 2p, 2p and 3s and 3p, then 4s and then 3d. So if it has to be 3d, right, so which has the highest energy electron, so n is equal to 3 and L has been equal to L has been 2, because L 0 represents s orbital, 1 represents p orbital and 2 represents d subshell, right? So these are the subshells which you have. So n is equal to 3, L is equal to 2 will have the highest energy. Now after that, that single electron which you have, that could be in any of the m orbitals. So that would vary from -2 to +2. Correct. So that would be the magnetic quantum number. So if you see the options, only this one is the right match which we can find. Okay. The next question, it says that penultimate and outermost orbital of an element has 10 and 2 electrons. If the outermost orbital is fourth orbit, the atomic number of this. Okay, now check this out. When you have n is equal to 1, n is equal to 2, n is equal to 3 and n is equal to 4. If this is the ultimate orbital, shell, then this will be penultimate shell. So in 3 we will have 3s, 3p and 3d subshells. 4 will have 4s, 4p, 4d, 4f. Now out of these 4, if you check out the one which has lowest energy, that is 4s. So those last 2 electrons which is given there, they must be in 4s. If they are in 4s, the rest of these orbitals will have their 10 electrons. So which includes, again, 3s will have first 2 electrons, 3p will have 6 electrons, and the rest of the electrons which are present, right? So we'll have this many, and so you need to check out the number of electrons in 3d now, right? So we'll have 3d will have how many electrons? We already have 6 plus 2, 8 and another 2 electrons here, right? So total 10 electrons are been done. So 3d2, so there should be configuration something like 3d2 and 4s2. That will be the atom's last configuration, which is nothing but titanium 22, which says argon 4s2 and 3d2, correct? So this would be the titanium. So the atomic number for titanium is how much? 22. So that would be the case. I hope you understood that. Let's see this next question. It says that which of the following ion will have maximum magnetic moment? See, magnetic moment would be maximum when number of unpaired electrons are maximum. So our objective should be about finding out number of unpaired electrons. See, Fe, which is 26, will have a configuration of argon 4s2 and 3d6. Now, if 3 electrons are lost from here, this will become 23, which is argon. First 2 electrons will be lost from 4s and 1 electron will be lost from 3d. So therefore the number of unpaired electrons, now if you observe, they are 5 of them. Okay. So if we see the next one, chromium, which is supposed to be 24, argon 4s1, 3d5. And if it loses 3 electrons, becoming chromium 21, so we will get this as argon 4s. I'm writing this as number of electrons, don't worry about the protons, okay? This 23, 21 are number of electrons. So now I'll have 4s0 and 3d3, so which means I have only 3 unpaired electrons this time. So here the number of unpaired electrons are 5, here the number of unpaired electrons are only 3. Similarly, if you check out titanium 22, which is supposed to be argon 4s2 and 3d2. Suppose if it loses all 4 electrons, then it will become titanium plus 4. So it will simply be argon 4s0 and 3d0. So number of unpaired electrons are 0. Cobalt plus 3. which is supposed to be 4 is to 3d7, right? Now if it becomes, sorry, this is cobalt. If cobalt becomes cobalt plus 3, this will become 4s0 and 3d6. See, 3d6, it would have 1, 2, 3, 4, 5, 6. So the number of unpaired electrons would be only 4. So our question is, which one will have maximum number of unpaired electrons, because that would have more amount of magnetic moment. So our answer should be A. Okay guys. See the next question. The magnetic moment of nickel, so this nickel X plus is given and the magnetic moment for this is 2.82. See, by formula, magnetic moment is n into n plus 2, where n is number of unpaired electrons. That is given as 2.82, which implies if I square on both sides, it is n into n plus 3, which will be equal to 8, right? So from here, if we calculate n into n plus 2, yeah, if we calculate n, so n square plus 2n minus 8 equal to 0. So that will give us n is equal to 2, correct? Right. So now we got n is equal to 2, which means number of unpaired electrons are 2. See, if nickel gets plus 2, then we'll have 4s0 and 3d8. In 3d8, if you see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So we can clearly see there are 2 unpaired electrons, and these 2 unpaired electrons are responsible to get this dipole, to get this spin momentum. So therefore x has to be 2 so that we can generate this mu as 2.82. Got it?